In this video, we're going to learn about populations in objective space and decision space. In single objective problems, the objective is to find a single candidate solution which represents the global optimum in the entire search space. Multi-objective problems often involve conflicts between multiple objectives, and as a result, it's unlikely that there exists a single optimal solution. Therefore, the solution to a multi-objective problem can't be a single candidate solution, but instead a set of candidate solutions which represent the optimum trade-off surface in the objective space. This set is referred to as an approximation set, as it's an approximation of the theoretical optima. Speaking of evolutionary algorithms, you can support this work by getting the book on practical evolutionary algorithms. It's a practical ebook that takes you from the concepts to how they're implemented using Python. You'll get all the Jupyter notebooks, unlimited updates, and of course, these supplementary video tutorials. Check out the link in the description. You will also find a link to my Twitter and the Discord channel where you can make requests and get support. Throughout the optimization process in an evolutionary multi-objective optimization algorithm, a population of solutions is iteratively subjected to various operators until termination, at which point this final population, or subset, is determined to be the approximation set. Let's introduce and describe these concepts through a demonstration by generating a population of decision variables and using the ZDT1 test function as the objective function. We'll describe these concepts mathematically and implement them using Python. Let's begin by defining our population size as n equals 50, our number of decision variables as d equals 30, where each variable falls between 0 and 1, and number of objective values as m equals 2. Let's now define our population X containing n candidate solutions. In this case, a solution X with the subscript lowercase n refers to the nth solution in the population, and each solution is made up of d decision variables. Let's initialize this population with random decision variables, making sure to take into account our upper and lower boundaries. In the same way, let's define the corresponding objective values y of the population X. In this case, n refers to the number of objective value sets, and each objective value set contains m objective values. In the case of ZDT1, that means 2 objective values. To generate y, we'll need to evaluate each solution in X using the ZDT1 test function defined above. Finally, let's visualize each of our 50 solutions in objective space using a scatter plot. We could also visualize our 50 solutions in decision space, although it's not very useful at this point. That's it for this video on populations in objective and decision space. We covered how to generate and visualize a population in the objective and decision space using the ZDT1 synthetic test function. You'll find many different styles of mathematical notation employed to describe populations in the evolutionary algorithm literature. However, you should be able to understand them if you learn the ones described in this video. Speaking of evolutionary algorithms, you can support this work by getting the book on practical evolutionary algorithms. It's a practical ebook that takes you from the concepts to how they're implemented using Python. You'll get all the Jupyter notebooks, unlimited updates, and of course, these supplementary video tutorials. Check out the link in the description. You will also find a link to my Twitter and the Discord channel where you can make requests and get support.